Let's go over all the variables we control in a thermal simulation or human comfort simulation in Climate Studio. First, it's important to remember that our architectural model is not always the same as the geometry that we're going to simulate with. So for example, let's say this is our architectural model here. This is the space we're designing. And we have a thickness to our envelope. There's tons of other ways we could have a more complex shape than we would need for a thermal analysis. Because in a thermal analysis, all we're concerned with is the surface area that surrounds the volume of air that is the zone that we are simulating. And that's true because if we, let's say this envelope here were 2 foot thick and made of concrete, or 6 inches thick and made of some kind of really insulative material, it would have very different characteristics from a heat flow standpoint, but the surface area that heat is moving through would be the same. It would be the exterior of the envelope. So that way we can, by having just surfaces that we're defining for our thermal model, we can change the envelope, for example, and compare without changing anything with the geometry. So that's why we're using the surface area. So then let's just run a quick model and look at the variables. What do we need then to run a model? Well, not much. We need climate data, which I've already downloaded. We're at New York LaGuardia, and I need to be in the Thermal Analysis tab in my Climate Studio workflows. I come to, by the way, too, I'm always going to be, I'm often going to be in IP units, which is what we use in the US. So just be conscious of a way to toggle this really easily is always to come, this sort of summary is always a tab here, so you can always come back to that quickly no matter where you are and change the units, and it will change it for everything. That's just for by the way, that's just for Climate Studio, not for Rhino. If you want to change your Rhino units, you have to come to units, right? So it's just, those are 2 different things. I'm in feet in my general model. Okay, so if I come to my thermal analysis tab, and but now this is my architectural model, so I have to create a thermal model, which I've already done. I have created this zone, which is the same geometry as my architectural model. It's just surfaces, right? So I only have a single poly surface. I'm going to select that from my zones tab, hit enter, and this dialog appears. Well, actually, what is this? This is a huge list, and these are just templates that are different collections of the variables we're getting ready to talk about. So once you start modeling, you can use these templates to compare different types of standards. So like 90.1 is a specific energy standard. I've created some for myself down here that are to the Pascal standard. I created a 1960 baseline, sort of just all concrete with incandescent light bulbs template. So the idea is that once you get adept at this, you can just change your templates and very quickly compare different configurations. So it's very powerful. I'm just going to select this first one up here, residential multifamily housing, just because it doesn't matter. Say OK, and now I have a zone here. If I open that zone, we'll see that I have a bunch of facades. If I come over here to wireframe, I can click through them. So there's all these different facades. There's an exterior floor and a roof. We'll talk about what those are in a second. Okay, so let's look now then at what we have by picking that template. What we have, what we're defining, what variables we're controlling. So I'm going to go back and edit this zone, and this is what the template chose. We have 4 tabs here: loads, conditioning, envelope, and settings. Actually, I'm going to go back and I think it's good to start with these closed because they're summaries. And let's just go through all of these. Now, we're not engineers, We're not expected to understand this in depth, and we never want to assume that we're, we could be doing this wrong, right? I mean, we always want to be talking to people who do this for a living. But for us as architects, it's incredibly powerful for a variety of reasons. One is that it helps us design in a way that when the engineers do get involved, they're not saying, well, that's cute, but we can't do that for this reason, and then they, take control. This allows us to design in ways where we're not creating things that can be value engineered out that we want to keep in. Lots of good reasons for becoming adept at this. So what I'm saying is, not expecting you to be an expert, but we need to understand the basics of these variables. So what's going on here? Why do we have loads, conditioning, envelope, and settings? And by the way, these are just the terms they use. There's different ways of conceiving of these things. In the Climate Studio, loads, this essentially means things that are creating heat or using energy in the building. So let's go through those. First, people. Why are people is part of loads? We're not talking about live loads here on floors. We're talking about heat. People, we're little furnaces. We create heat because we're always, burning fuel to move around. So we need to identify how much heat is being created by the people. So that means we need to know how many people there are per square foot. This is something that was determined by that template we chose, and it's going to obviously a warehouse or a multifamily house or a single family house or a bowling alley are going to have different people densities. Okay, so that was set by our template. What's this metabolic rate? Well, like I just said, we produce heat. You produce heat at rest, but of course you would produce more heat if you were running around. So we have to say, what is the basic activity level in the space? So we use this metabolic rate variable. In this case, we're using these all have to be standardized. So this ASHRAE is a standards organization. So this is a specific ASHRAE standard for dynamic clothing, and the unit is called the CLO. Whatever, we don't need to know the specifics of it, but in this case, 1 would be completely at rest. 1.2 means that we have some activity. If we were in a warehouse, this would be higher, right? So that's determining the amount of heat that the people are generating. Then we create a schedule for it. So we say, when are the people going to be in the space? If it's a warehouse and people, or if it's an art installation that's only open 1 day a year, that's going to have a very low person load. If it's an ice skating rink, that's going to have a different one. So in this case, we see that, so at night, people here, right? Obviously they're sleeping. Then they go to work. Here, there's people coming back for lunch, I guess, or maybe there's more maintenance people in the building at that time. There's these are standardized also, right? So the point is that we schedule, we have a load. These are people. We say when the load is there. There's also an airspeed variable. We're not going to worry about that. We can talk about it later. It's a little more nuanced. It's fine to leave it at 0. Equipment. So we have something called equipment power density, and we have lighting power density. You hopefully have heard of lighting power density in environmental systems, but if not, fine. The basic idea here is that equipment is going to use power and it's going to create heat. So we need to quantify that, and in this case, we're quantifying it in watts per square foot. So it's just basically a general summary of how efficient our equipment is, how much of it there is. And this again, there'll be standards for that are, if you're really, really dialing into this, you could customize it. If not, there's going to be a number that's going to be predetermined based on the type of space that we're talking about and the standard we're trying to meet. And then we'll of course also schedule this based on when it's going to be used. And so let's not even get into that. Just say that there's obviously a ton of different ways this could be configured. So we'll always schedule that. We'll always schedule our equipment power density measurement. Lighting power density is the same idea. We have light that we're using in the electric light of some kind that we're using in the space. How much of it? So like in a warehouse, it's going to be different than in a library, obviously. Also, how efficient the lighting is. So incandescent light bulbs, which are basically heaters that give off a little bit of waste light. would have a much higher lighting power density with the same amount of illuminance as LEDs. And so this number might change drastically based on the equipment we choose. So one of the points here with loads is that these are things that are going to change as we change them and make the building more or less efficient. The geometry won't change, right? So a lot of that's true here. And so these are things that we might, once we've decided, well, this is the level we're going to be at, we would set them to these specific levels and leave them and iterate other things that are more architectural. But we still need to know what they are so that we can determine if we're meeting our end goals, which is going to be some standard that we've defined. In this class, for example, local law 97 is what I'm saying that we're going to make our standard for energy usage, and that's because it's what we have to do in New York City right now, and it's pretty stringent. So anyway, we would schedule our lights when they're on. They're going to be on during the day. In this case, in a building, a residential building. People go to bed, they're saying here at 11, getting up at 6 as a general rule. We also set an illuminance target. So based on the kind of space it is, how much illuminance we generalize is required at each surface. So if it's a place that needs very detailed works being done, that maybe it's going to have a higher illuminance target than again a warehouse or a movie theater. And obviously, higher number there is going to create more power usage and more heat. Then if we dim or not, that's a very important, but this is just a button we choose because dimming is going to allow us to save energy. And this is based on photocell control. So we'll talk about that at some point. But anyway, basically, this is how much lighting is affecting power usage and heat. Hot water, yeah, I mean, I maybe would have put that in conditioning, but I get it. The conditioning thing is going to be about just the space itself. So they put it here. We're basically saying that we're going to need to make hot water, and it's going to require a certain amount of energy. I don't think the heat that the hot water is giving off is part of this. And we can look at that and check when we look at the outputs. So we're defining the inlet water temperature from the city, what our set point is for the water coming out. We're also going to schedule this. We can change the flow rate per person. That's also typically a standard. It's based on, if you're in a gym as compared to a museum, those are going to be very different, right, in terms of how much water a person's going to use who's occupying the space. This is a really important unit here, COP. So let's talk about it for a second if you haven't heard of it before. COP stands for Coefficient of Performance. And it is, so for example, in Local Law 97, if you have a building that you need to upgrade to that standard, and you don't want to do a bunch of intervention on the architecture, the first thing you're going to look at is how do you save energy with your mechanical systems. And COP is a very basic metric for that. So a COP of 1 essentially means that you're putting in one unit of energy, so a fuel, and you're getting 1 unit back. So electric resistance heating is typically defined as having a COP of 1. Gas, for example, is going to have a COP of maybe 0.7, 0.8, 0.9, could be a little higher, because you're not getting all of the energy that you burn. There's going to be some waste, going up through the flue. Heat pumps, however, can have a much higher COP because they are not creating energy or creating heat, they're moving heat from inside to outside or outside to inside. Your refrigerator, for example, is cold because it's pulling heat out of the air inside the refrigerator and dumping it into your apartment or wherever the refrigerator is. So anyway, we can have numbers that are higher, and it's very typical that that's a way that we would improve the energy efficiency of our building is by improving our mechanical systems. Hot water is one of the places we could do that. Okay, so that's our loads, the things that are creating heat. It's just the stuff that's creating heat and using energy in the space. Now, the next tab here, conditioning. What is this talking about? It's basically our HVAC system. So HVAC is going to heat, is going to use energy, it's going to produce heat, so it's also a load. But what we're talking about here is what is the system, what are the settings that we, what is the interior environment we want? So what are the settings going to be? And what is the machinery we're going to use to create that? Now, this is a pretty basic model, even though there's a lot to it and a lot of fun things we can do with it. So we're not defining our mechanical systems in a lot of detail, but it's still very powerful, and we still need to be very conscious of what we're doing. So we have a set point, which basically means this is the temperature that we want our interior air to be. Now, why 66.2? I'm sure it's because that's converted from Celsius, right? So just like, why is it 98.6 is human temperature, you know, our body temperature? That's because that's converted from Celsius. Anyway, so that's why 66.2. It's on constant because we're just going to have the mechanical system always on and just being turned off based on when we get to these temperatures. There's other ways we could do it. There's some other variables here I'm not going to talk about. But again, here's COP. So right now we're just saying this is a basically, you know, be electric resistance. That would never be the case, but I think they're just kind of saying, well, it's going to be some basic. That's a baseline. Okay, so heating, we've got a set point, we've got basic information about how we create the heat, and we can schedule it. Which will, if we were to schedule this, we would be able to reduce our energy usage more or less based on our situation. Cooling is exactly the same thing. We have a different, you notice the set point's pretty high. That's typical in, I'm a little surprised by that in a multifamily house, but I mean, so anyway, this is just an example, or multifamily building. One thing I didn't mention was this, you know, the max heat air supply and the minimum cool supply air temp. This is a way of just giving a little bit of information about your mechanical system. So, for example, you know, if this were a boiler, we'd probably have a higher supply air temperature because they tend to be hotter. Again, this isn't a mechanical engineering class. We don't have to get into that. Just letting you know that there's a lot of fine tuning here that can be done, which is a good reason to use standards. Again, we have COP here. So we could, and cooling is a place where even if you're still just using a boiler for your heating, very often you're going to use some kind of air conditioner that has got a compressor, which is going to be a heat pump, which is going to have a higher COP than one. We also can control humidity. Right here, the preset is typically between 80 and 20 relative humidity. We can talk about that if you don't know what that really means. I don't want to get into it now, but you know, it's a comfort variable. It's also a durability variable for your envelope. It's off here, which kind of surprises me. That might be because of the climate that they were assuming they were in, or I don't know, there's some other reason. We'll definitely turn it on eventually when we're doing a more detailed model. Mechanical ventilation. And so what is that going to change? There's going to be fans and other equipment that's going to have to be on if that's turned on, and so that would change our energy usage and heat production. Mechanical ventilation, we have to have fresh air to live, and so we are always bringing fresh air in and exhausting stale interior air. That, of course, uses energy, and it also brings in, if we're bringing in 30-degree outdoor air into a room that we've just heated to 70 degrees, we're going to lose energy that way. That's why, in this case, they've turned on heat recovery. In classes I've taught in environmental systems, we've talked about that to some degree. I'm not going to talk about it right now, but just realize that there are more settings here for mechanical ventilation that will allow us to be more or less energy efficient. Like they have an economizer on, which means when the outdoor temperature or outdoor conditions are close to the interior comfort zone, they just turn off the ventilation or they turn off the heat recovery and just bring in fresh air. Anyway, so there's some nuance to this, but right now we're just saying that there is a place where you can go to set the amount of mechanical ventilation in your building. Then we can also set natural ventilation, which is a fun thing to play with, and that'll be a whole separate little workflow that I'll go over at some point. Okay, so we have here's the stuff that's creating heat and using energy. Here's the stuff that's producing our interior environment, and it's also using energy. Now the envelope, this is where we prevent the flow of heat from inside to outside and outside to inside. Once we've spent a bunch of energy and money and time trying to create a different environment inside, we don't want that just to leak outside, right? So how do we do that? First, we have what this I think is a European term, constructions, or maybe it's just a translation from something. We would call these assemblies. And there's a variety of assemblies: roof, facade, partition, slab, external floor, ground slab, and ground wall. You have these nice little icons here explaining, roof's obvious. Facade is basically any exterior wall. Partition is an interior wall, and then slab is slab here because it's concrete. If we changed the envelope inside, we could have a different name there, but it's basically whatever is a floor that's inside the building. We might have an exterior floor like this little cantilevered space here, and then a ground slab and a ground wall are constructions that are touching the ground, and we can change these very easily. So let's just look at how that works. So if we're this is a preset that we in the template we chose. For the roof, we can see here that we have different, we have a U value and an R value. Hopefully you remember the basics of this. And just remember we're in IP units. I can actually, this is cool that you can switch them here. So make sure, U value and R value are the same terms in IP and SI. So just make sure if you're looking at this that you know what you're looking at. And U value is usually an assembly value. R value is often for single materials, but the basic relationship is that they're the reciprocal of one another. So, for example, if I divide 1 by 0.035, get 28.5, and this is 27.449. That could be a conversion because they're always in Climate Studio. They're European in their basis. They're always going to be starting with SI and converting. But I think this might have something to do with thermal capacitance because we have concrete, and concrete has thermal mass, which, anyway, I don't want to get into that. But just letting you know that it's close enough, so I think that's right. It's just there's something else going on. But what were we saying? Basically, the assembly that we chose in the template is called U value 0.2 mass, which is just you can see 0.2 it's not 0.2 here, but if we change to SI, it is 0.2. So there's a little bit of, you got to get used to this. Practice. I would play around with simple models before you start doing this in your studio projects, and you pretty quickly learn the idiosyncrasies or just the way it works. Anyway, so this is they called it 0.2 mass because that was how they were thinking of creating relationships in their minds between these different assemblies they were making. And we see that it's made of concrete on the inside and mineral wool insulation on the outside. If we want to change that, we can actually pick something else, or we can make our own. So I can duplicate here. I'm going to call this test. And now I can edit it. And I can, if I select, let's say I don't want concrete anymore. I want it to be some kind of insulation. No, I'll make it some kind of wood. See, some of these, okay, I'll just make it wood stub and fiberglass, and I'll get rid of the mineral wool. Now I have, and I can change the thickness. This is in feet, so this is like a little bit, this is a more like a 2x8 or between 2x6 and 2x8 wall, and we have an R value of 25. And oh, and by the way, there's also these values. Actually, let me go back into the other one. I'll deal with that in a second. Point is, we can change these. We can make our own. And once you've made one, it becomes part of your library. So this whole thing that we're dealing with right now is the library. So it's very powerful because we can customize. So in your own studio projects, when you get to that, if you're using CLT, you can make your own CLT envelope in Climate Studio and test it and compare it to concrete and see what the advantages are. One advantage or disadvantage you're going to find is that we have embodied carbon and embodied energy as variables that they're including here. So we can, one of the advantages of wood is it's carbon negative usually, whereas concrete's pretty carbon intensive. So we might get a real advantage there by using wood over concrete, and we can measure that in Climate Studio. Okay, so anyway, we have these different constructions that we identify here. And then, like I said, they're going to have the same, we don't have to change the geometry because the exterior surface that the heat is moving through, that these envelopes are resisting, is going to be the same size regardless of what the envelope is for this design. What else can we do? We can add an additional internal mass. So so in other words, everything is going to have mass, and that's being considered. Let's go back to this. If I'm looking at the roof, you see they said thermal capacitance here. That's mass. And so they're trying to, let me just go ahead and say this basic building science thing. To code in the US, building assemblies, their resistance to heat flow is determined only by their R value, which is does not take into consideration how much heat the material can hold. So dense materials are penalized typically. So they're trying to bring in mass as part of the thermal calculation, which is awesome. So there is already going to be that calculation in, and I think that's why this R value is different than when I did the reciprocal of the U value. Anyway, so they're trying to bring that in, and so that's going to be just part of whatever materials we choose. It's going to be some kind of thermal capacitance, capacity to hold heat. But we can also add extra. So, for example, if we were saying I'm going to have a trum wall, and I'm going to have a bunch of mass in a wall inside some glass, I can estimate how much that is and include it here and get some kind of thermal change in maybe an advantage, may not be. So that's what additional thermal mass is. Infiltration, hugely important. We should talk about this in a separate context because I don't want this to be too long. But think about it. If we're talking about the heat moving through this envelope here, and we're creating, we're controlling all these variables, and specifically in the envelope, we've carefully designed the different layers in a way that we think will help the thermal performance in a way that we want it to. If we have a bunch of holes in that envelope, then it's really undercutting our efforts. So the contemporary approach to architecture is to be as airtight as possible within budget, pretty much. Usually that's the case. There's there's exceptions. And so this is a very important setting. There's air changes per hour is one, ACH, and there's also air changes CFM per square foot, so flow per exterior area, CFM per square foot. That's basically saying how much leakage per square foot of this exterior envelope. Either one of these works. There's different reasons that they're used, and we can talk about it. But that's an important variable that you will want to adjust or just know about. And then foundation is finally just the way that we model any of the part of the building that's touching the ground. And so there's just different ways this can be modeled. We're using ground temperature, so that's coming from the climate file, information on how the ground is changing, the ground temperature is changing through the year. All we need to say about that. Okay, so we have the amount of the stuff that's creating heat and using energy. We have the stuff that's creating our interior environment. We have the stuff that's resisting the flow of heat and other variables from inside to outside. The only other thing we need to talk about is what they're calling settings here. And these are basically the costs. And this is going to be really important. Cost is, obviously huge for everyone. And And in our case, cost means both carbon and money. And there are presets here that we will change based on local law 97. And if we want to get into actual costs of our energy, we'll look these up and adjust them based on whatever jurisdiction you're in. But the point is, we're setting these here, and all they're doing then is just, they don't change the performance, they just change how much carbon and how much money is required for our design. Very important, but it's just a setting, it's not changing the performance. Okay, so now I'm going to close that. And what we've done is done a very quick zone model and gone over all the variables that we control in our design to adjust our thermal performance. Next, I'm going to talk about the outputs in another video.